In this presentation, we demonstrate the various applications of our proposed representation learning method via global temporal alignment and cycle consistency. The various applications enabled by our approach include video synchronization, 3D pose reconstruction via alignment, fine-grained retrieval in videos, and finally, fine-grained audio-visual retrieval, where we can use a specific moment in an audio signal, such as this one, and the desired output is to extract the corresponding visual segments. We will now discuss each one of these applications in more details. Starting with the most direct application of our alignment approach, which is video alignment. In this application, the goal is to synchronize different videos depicting people performing the same action. In this first example, we are given two sequences of a pull-up action performed by different actors in different environments and at different execution rates. Note how the actor on the right is slower at performing the pull-up action. Now, given a model trained using our alignment loss, we extract frame-wise embeddings from both sequences and use them to find the optimal path that aligns the sequence on the right side to the one on the left side. This results in aligned videos, where the actor on the right now performs the pull-up action at the same execution speed as the one on the left. In this second case, we show an example of a baseball pitch action where the action is also performed from two different viewpoints as well. As opposed to the previous example, now the actor on the right side finishes much faster than the actor on the left. Going through the same alignment process, we can see that our approach is capable of aligning videos in this scenario as well. Notice how in this case, the actor on the right side slows down in order to allow for the actor on the left side to catch up. This is especially interesting given that the actors also have slight variations in the way they perform this baseball pitch. Next, we show an even more complicated example with two videos showing gymnasts performing a vault event. In this case, the video on the right shows a face close-up of the gymnast while she is running towards the horse, while this is not captured at all by the video on the left. Note here that the obtained alignment learns to skip over the close-up frames as they don't exist in the video on the left, and to make up for skipping those frames, the gymnast on the right now pauses before jumping in order to allow the gymnast on the left to catch up and reach the same phase of the action. Finally, in this final example, we show that our learned embeddings and the resulting alignment path also can handle repetitions within an action. In this case, the two gymnasts perform a different number of saltos and at various speeds. Through our learned embedding, the alignment path now forces the gymnast on the right to pose such that both gymnasts hit the floor around the same time while performing this floor exercise. More generally, we can show that our alignment-based loss leads to learning strong embeddings capable of aligning videos of various actions irrespective of differences in the backgrounds, action execution rates, camera viewpoints, or even slight variations within the sub-actions themselves. Now, to understand what is being learned in our embeddings and what allows for finding these alignment paths, we now show visualizations of the learned features. For this purpose, we extract feature maps from the last convolutional layer of our embedding network and use the class activation map method to visualize features pixel-wise. On the left side, we show an example from the golf swing class in the pen action dataset. And on the right side, we show an example from the vault event in the fine gym dataset. In both cases, bright red corresponds to high activations, whereas blue corresponds to low activations. Now, careful examination of the golf swing example reveals that in this case, the learned embeddings are selective to body parts involved in performing an action, such as the lower part of the body in the beginning and the upper part of the body towards the end of the action. On the other hand, for the vault event, we note that the learned embeddings are selective to human contact points with surfaces, focusing on the floor towards the beginning of the action, the contact point with the horse in the middle, and the landing point towards the end. More generally, these visualizations suggest that the proposed loss learns to adapt and identify the most reliable and consistent cues to learn the alignments. We now continue and show further downstream applications of our alignment-based approach. Here we first start by showing the 3D pose reconstruction application. Given an input video, we start by aligning videos of the same class to it, and we also extract the 2D key points from the now aligned video frames. Note that the aligned videos depict the same action captured from various viewpoints. Using the aligned 2D key points of the pose captured from different viewpoints, we obtain a 3D reconstruction. The 3D reconstruction is obtained using the bundle adjustment algorithm initialized from the factorization method of Tomasi and Kanadi. Notice how the 3D reconstruction is also aligned to the video. This reconstruction also works for more complex actions such as baseball swing. Importantly, note that the reconstructed 3D pose in this case corresponds to the average pose across different aligned videos due to the variations in which a baseball swing is performed by different actors. We now show another application of our alignment, which is fine-grained retrieval in videos. Given any query frame capturing a given phase of an action, such as the two phases shown here on the left, we can find frames depicting the same phase of the action from other videos of the same class by extracting, for example, the top 5 nearest neighbors of such frames in embedding space. Here we show examples from the baseball swing class, but this behavior also extends to other classes with various levels of difficulty, such as baseball pitch, a balanced beam sequence, or a vault event sequence. Finally, we also demonstrate that our alignment-based representation learning method can be applied to other types of temporal sequences by jointly training an audio and a visual network to learn the alignment between the two modalities. The embeddings learned through this alignment task allow for fine-grained audio-visual retrieval. For example, given an audio segment corresponding to the moment of firing a cannon, such as this one, we can find the corresponding visual segment by using the audio embedding as a query and retrieving the nearest neighbors among the visual embeddings of the same class. Here we show the top 5 nearest neighbor of this specific audio query. Once again, we can show that this behavior extends across various audio queries. Here we show a second audio query and the corresponding retrieved visual segment.